Buonasera a tutti, sono Tommaso e sono uno dei volontari di Bergamo Scienza. Prima di iniziare vi chiediamo un momento di attenzione e vi ricordiamo che collegandovi al sito bergamoscienza.it e cliccando sul pulsante live sarà possibile pubblicare su Facebook e su Twitter la diretta dell'evento, inviare anche domande ai relatori che verranno lette dai nostri volontari e invitare i propri amici e i propri follower a seguire la conferenza. Per la traduzione simultanea trovate sulle porte all'ingresso della sala un QR code tramite il quale accedere alle traduzioni simultanee per poter ascoltare l'evento. Il QR code vi reindirizzerà con verso web app dove potrete selezionare la lingua di interpretariato dalla tendina. Per ascolto è necessaria una copia di auricolari. Se li avete potete usare i vostri, altrimenti i nostri volontari ne hanno una copia a cui potrete chiedergli. Vi chiediamo inoltre di silenziare gli apparecchi elettronici e di partecipare numerosi alle nostre iniziative. Grazie a tutti per l'attenzione.
Buonasera a tutti, benvenuti. Devo dire che è una grande soddisfazione vedere una sala piena di mercoledì sera. D'altronde c'è la Juve e il Milan, calcio minore, che noi Champions non siamo abituati a seguire, però vi ringrazio per essere qua così numerosi. Stasera parliamo di un tema particolarmente rilevante per tutti noi. Abbiamo intitolato questa conferenza "La pandemia silenziosa, come la medicina può arginare l'ondata imminente di malattie di Alzheimer e in generale delle forme di demenza che, ahimè, se guardiamo i numeri, è diventata una vera pandemia. Purtroppo man mano aumenta l'età, o per fortuna man mano aumenta l'età media di aspettativa di vita, aumenta anche l'incidenza di queste malattie, poi ne parleremo. Abbiamo stasera la fortuna di avere qua uno dei più grandi scienziati al mondo che si occupa di queste malattie, Gregory Pezco, di cui vi racconterò brevemente alcune tappe della sua carriera, perché sarebbe difficile veramente raccontarvi tutto. Greg prende un Bachelor in Science a Princeton University, dopodiché completa il suo percorso di studi al Merton College all'University of Oxford in UK, dove prende un PhD, prima un Master e poi un PhD in biochimica, e da lì inizia la sua carriera che lo porterà nei più grandi e prestigiosi istituti del mondo, dall'MIT a Cornell University ad Harvard, dove tuttora è professore di neurologia. Lui ha sempre cercato di provare a studiare in realtà quali sono i meccanismi biochimici che in qualche modo possono essere alla base di queste malattie, perché spesso, purtroppo, nella pratica clinica diagnostichiamo troppo tardi queste malattie, non riusciamo ad avere, diciamo così, o a prevedere quali sono le persone che un giorno potrebbero incontrare questi problemi, e quando in qualche modo riusciamo ad incontrarli spesso è troppo tardi, perché purtroppo il cervello ha già subito danni particolarmente importanti e da un certo punto di vista irreversibili. Quindi il professor Pezco nella sua vita si è occupato di queste malattie cercando di capire quali sono i meccanismi a monte di queste malattie, cioè quali sono poi le reali cause che determinano la morte di queste cellule che portano a quella che è l'atrofia cerebrale, che è il sintomo, diciamo, più evidente di queste malattie e che appunto ci aiuta a fare la diagnosi, ma quando l'atrofia è già intervenuta, appunto noi facciamo la diagnosi e quindi è troppo tardi e ci vorrebbe qualcosa che in qualche modo evita questa progressione così, diciamo, importante. E nella sua carriera ha studiato non solo la malattia di Alzheimer, ma tutte quelle malattie come la malattia di Parkinson, la sclerosi laterale amiotrofica e quelle altre forme di demenza che fanno parte di queste cosiddette malattie neurodegenerative, che sono proprio la pandemia di cui andremo a parlare. I suoi contributi sono tantissimi e anche le sue onorificenze, i suoi premi, però noi siamo abituati a evitare prologhi particolarmente lunghi, anzi tendiamo a favorire la discussione dopo, quindi io non voglio perdere altro tempo, sono molto felice che Greg è qua da noi, che ha voluto venire e che ha accettato il nostro invito. So, without any further delay, Greg, thanks for being here and the podium is yours. We will be listening to your talk. Grazie ancora.
Yeah. Mille grazie. That is about the only Italian I will use. I am sorry. I want to talk to you about a new kind of pandemic. Not one that comes from a virus, but one that comes from all of us as we grow older. And I want to tell you how we, as medical scientists, and there are people that I'm working with here, John Vito, for example, Luca Muzio, Pier Fausto Senesi, all from this area. We are working hard to solve this problem before it becomes a pandemic. That's the story I will tell you tonight. We must begin by listing the various companies that I am associated with. This has nothing to do with the talk, but I think it's a good idea that you know that I do have relationships with biotechnology and pharmaceutical companies. Now we begin. This is my grandson, 1 year old. And this is his great-grandfather, my wife's father, 84 years old. I never knew most of my grandparents. They died before they were 60 years old because they were born in the 19th century, and people in the 19th century did not live long. But most children born today are going to know their great-grandparents. And that has never been true before in the history of the world. When my grandson was born, the world looked like this. And only these countries, including Italy, had more than 20% of the population who would be considered older people. That's today. But when my grandson is 30 years old, he will be living in this world. Wow. One reason for this is, as I said, people are living longer. When my grandparents were born, life expectancy was less than 50 years old. Now, you can live to be 80 years old, and it's continuing to increase. You will be here in this auditorium 1 hour listening to me, and during that time, your life expectancy will increase by about 1 minute. Prego. But there is Petsko's fourth law. If something is good, it can also be bad. And this is true with living older. Watch this movie. All right. I will start it from here. What you see here is the age distribution in the early part of the 20th century. Lots of children, not so many older people. But now watch as we get closer to today. You can see the baby boom, and the baby boom will be moving through. But watch what's happening to the overall shape. You see, it is very different. And it's getting more different. And now, it's beginning to become flat. And as we get closer to when my grandson will be 30 years old, you can see what has happened. And if I played this further, this would all be flat. Notice, these are people 80 years old. When I was born, that was considered very old. But now look at this. Here is another movie. Here we have the number of children that a woman had, and here we have the life expectancy. And in 1800, the average woman had 6 children. Maybe somewhere in here is Italy. All the countries are here. And the average life expectancy was 35 or so. Now I'm going to play this movie and watch what happens to the life expectancy and the number of children. So, as the years go by, not much happens until we have good public health. And then things begin to move. Clean water, clean air. Now people are starting to live longer in much of the world. And now we have antibiotics. And now things move much faster. You can see that, and they're heading for up here. And as we get to this century, most of the world is now here, above 65 years of age, even in parts of Africa, and they're catching up. And the average woman has a little less than 2 children. This is demographics in the 21st century. And it is not like anything that the world has ever seen before. The world has reached peak children. Right now, there are 2 billion children in the world, and that is all there will ever be into the future as far as we can see, unless something big changes. 2 billion children. But the population will continue to grow because more people will live longer. That's what I'm talking about. And you can see, while children have peaked, the working age population, 20 through 64, is actually declining. And now comes the most remarkable statistic of all. The fastest growing population group are people over the age of 80. When I was born in the United States, there were not even 2 million people over the age of 80. Now there are 13 million people over the age of 80 in the United States, and 30 years from now, 32 million people over the age of 80 in the United States. That is 1/10 of the population. That is extraordinary. And here's the problem. The problem is life is a Ponzi scheme. A Ponzi scheme is a fraud in which you pay money to someone who pays you money in return, but he is not investing your money. He is simply paying you from the new people who invest with him. And so as long as more new people invest with him, he can keep paying you money. And this is exactly what life is like. For 10,000 years, life has been with a lot of healthy, young, working people taking care of a small number of older people. Because there are so many more of them, they can take care of these people as well as themselves. But this only works if more people come into the system and other people leave. That's the Ponzi scheme. But look at what's happening. Today, as I showed you on that movie, this is starting to become flat. And in 30 years, it will be almost completely flat. And now we have the problem that there are not enough healthy young people to take care of a lot of very sick, very old people. Most things that you don't want to have become more common as you get older. You'll hear about cancer tomorrow from my wife. Same is true, heart disease, other things. But it's especially true of diseases of the brain. They are much more common as you get older, and they are much more difficult to treat than the kind of diseases you may have when you're young. Here's what I mean. This is your risk for getting Alzheimer's disease. You can see what happens as you get older. By the way, I know some of you are wondering, this is me right here. So you can see why I'm interested in this problem. By the way, this difference is real. More women than men get Alzheimer's disease, even if you adjust for the fact that women live longer. It's still more common with women. All right? We do not know why, and very few people are studying this. That's a mistake. This is very important, and more people should be studying it. Now, because I am 74 years old, I am wondering what's happening to my brain. And I am professor of neurology at Harvard Medical School, so I know people who are studying the brains of people who have died. And they have given me this picture. This is what the brain of a young person looks like, and this is what the brain of someone about my age looks like. You can see it's a little smaller, and you can see it's a very different color. And so I asked them, is this a problem? And these doctors all said the same thing. We don't know. But look at it. Do you really want to have the brain that has been in the oven too long? So there's no question that many changes occur in the brain as you get older. Some of them are okay, some of them are not. I'm going to tell you about one kind of change. It involves what is called dementia, which is the loss of your ability to reason. Dementia is an umbrella term. It talks about many different diseases. Alzheimer's is one of them. But Alzheimer's disease is the most common form of dementia. About 3/4, 75% of all dementia is Alzheimer's disease. So we have the big umbrella, and then we have different diseases underneath. Because I cannot take the time tonight to talk to you about all of these, I will only talk about Alzheimer's disease, which is the most common form of dementia and the one you are most likely to hear about or see in your own life. But these dementias, they do not care whether you are rich or poor, whether you are fit or not fit. Okay. Margaret Thatcher had Alzheimer's disease. The actor Robin Williams had a different type of dementia. The American football player John Mackey had a different type of dementia. The actor Dudley Moore, something else. And the musician B.B. King, something else. Race doesn't matter. Gender doesn't matter. Occupation. The one common factor, all of these people were relatively old. Alzheimer's disease, there's a lot of it. In the United States, more than 300,000 cases per year, and it goes with the population. So just divide this by about 5, and you have the number for Italy. Okay? After diagnosis, you don't live too long, but the last few years are not good. All right. About 5% of cases of Alzheimer's are due to mutations in a gene, and they are inherited in the family. But if you had that problem, you would know, because there would be a regular pattern of Alzheimer's disease in your family, and this is not common. Most cases of Alzheimer's disease are random, and we do not know a specific genetic or even environmental cause for those cases. All we know is that the people who get them are usually old. All right? And if you are looking for a reason to solve this problem, and your health and the health of your grandchildren is not enough of a reason, there's this reason. Right now, in the United States, 9 million people with dementia, about 6 million with Alzheimer's, of those 9 million. There will be 25 million with dementia in 2050. That is greater than the population of the state of Texas. So imagine in 30 years, the entire state of Texas filled with people who are demented. Actually, if you think about Texas politics, this may already have happened. In Italy, 1 million people with dementia in Italy today, about 700,000 with Alzheimer's. By 2050, 2.5 million, 1.7 million with Alzheimer's. That is twice the population of the city of Milan and about the population of central Rome. I will now make a political joke about this. Right now, Alzheimer's disease is the 5th leading cause of death in the world. I am excluding COVID because that's an unusual thing. All right? But if you leave out COVID, Alzheimer's disease is the 5th leading cause of death. 20 years ago, it was not even in the top 10. It's not on this list. Heart disease is still number 1. Stroke is still number 2. But Alzheimer's is now number 5. And in 20 years, Alzheimer's disease will be number 2. If dementia were a country, right now, there are 60 million people in the world with dementia. That's the population of Italy. Okay. By 2050, 135 million people in the world with dementia. That's more than the population of Russia. By the end of the century, by 2100, there will be 300 million people in the world with dementia. That is the population of the United States. If dementia care, the cost of these diseases to the public, to our families, to our government, to our medical system, if dementia care were a company, right now it would be the most valuable company in the world. More than Walmart or oil companies. That is how much we are spending on this problem right now. Can you imagine how much we will be spending on this problem in 30 years? And dementia is the only cause of death that has been getting worse. We have made, as you will hear tomorrow from my wife, we have made important advances in breast cancer and prostate cancer, in heart disease and stroke. Even things like HIV are no longer deadly diseases. But dementia, 70% worse in 10 years. Because we have no treatment for any dementia. No treatment. So what I have tried to describe to you is like an asteroid that is going to hit the Earth. And we know when it is going to hit the Earth. It is going to hit the Earth in about 30 years. And we have that much time as medical scientists to solve this problem for you. Because otherwise, your whole world will be changed in ways that are not good. So we as medical scientists are attacking this problem with everything we have. And I now want to tell you a little bit about that. Are we okay so far? All right. The first thing I have to tell you is that so far we have not done very well. In the last 30 years, 22 years, there have been about 200 clinical trials for Alzheimer's disease. 2 have succeeded, and they have not succeeded very well. Okay? This is a very bad success rate. But this is also a very hard problem. And one problem has been what I call the sunk cost fallacy. It means the more effort you put into one approach, even if that approach fails, it is hard to abandon that approach because you have put so much effort in. For example, one company here, when their trial failed, saw their stock price collapse. Now, you would think that would mean that they would abandon that approach. No, they put more money into that same treatment and tested it again and again. Because they had already put so much money into it by the time it failed, they could not admit that it failed. This is not a scientific problem. This is a problem of human nature. And it is very hard, even for scientists sometimes, to deal with this problem. But you need to understand that it is a problem we still see. Another problem is that it is very hard to model in animals a disease that affects old people. You make animal models of a disease in order to test your treatments before you try them on people. But a mouse lives 2 years. And we get Alzheimer's in our 70s and 80s and 90s. So to force a mouse to get something that looks like Alzheimer's disease, you have to do things to that mouse genetically that don't happen in people. So very often, treatments that will work in mice do not work in people. If you must get Alzheimer's disease, you should be a mouse. We can fix you. But it's not enough. Alzheimer's disease is named after this man, Alois Alzheimer, a German neurologist who lived around 1900. And this is the first patient he saw who had the disease that was named after him. Her name is August Dieter. And when she took this picture, she was 51 years old, and she had Alzheimer's disease. And she died with Alzheimer's disease at age 55. That's very young, because you see, she had a mutation. She was one of the 5% of people who had genetic Alzheimer's disease, and it ran in her family. Other family members had the same thing. This is the area of her brain that was affected first. It is the area for short-term memory. I'll show you more about that in 1 second. When she died, Alzheimer looked at her brain, and he found 2 things that should not have been there. Inside the cells of her brain, he found these tangles, which he called neurofibrillary tangles. And they are made up of a protein called tau. But outside of her brain, much bigger than these, were huge plaques, large clusters of brown material that he called senile plaques and that we now call amyloid plaques. And they are made of a protein called A beta. This was in 1910. For 100 years, everybody who was interested in Alzheimer's disease believed that this must be the cause of the disease. You don't see these things in a normal brain usually. So they are big and obvious. They must be the cause of the disease. Interestingly, Alzheimer himself did not think they were the cause of the disease. but everybody else did. And you can sort of see why. When proteins work, they work because they're folded into a specific shape. And the proteins that made up that plaque were in fact disordered. They were not in the correct shape. And so it was logical for scientists to believe these misfolded proteins must be doing some harm. They must be doing damage. But that theory was the basis for all of those failed clinical trials that I told you about. All those hundreds of failures were designed to clear the disordered protein plaque. Some of them even did that, but they did not cure the disease. And other diseases, other dementias, have plaque-like material as well. And once again, scientists are beginning to think maybe these are not the cause of the disease, maybe they are the consequence of the disease. Not the fire, the smoke from the fire. So why did they keep working on it? Well, one reason was they had put so much money and time in. But the other reason is what I call the streetlight effect. These are big and obvious. So there is an old joke in English about a man who is on the ground looking for his keys. And the policeman says, "I'll help you. Where did you lose them?" And the man says, "Over there by my car." And the policeman says, "Why are you looking for them here under the street light?" And the man says, "The light's better here." Well, the light's better here too. These are obvious and easy to find, so you could understand why people worked on them, but it's not the answer. These are the smoke, not the fire. Now, you may have heard in the last few days about a new result from one company, Eisai Biogen, about an antibody they have made against the plaques. And they showed an improvement in people who had Alzheimer's disease. But you have to understand two things about their result. The first was that it's only a relative improvement. Here's the people who did not take the drug, and here's the people who did. And you can see that they are doing better on this scale, but it's a small difference. And they're still getting worse. Nobody who took this antibody got better. Everybody got worse. They just got worse a little slower, about 20% slower. And this is true of all the other drugs that have been tried against the plaques. The ones that have shown any benefit at all have shown about a 20% slowing in rate of decline, but that's it. And what we want is this. And we're not seeing that with any drug yet. And I believe, and I would like you to think about the possibility that the reason is that the plaques are not the cause of the disease. They're the consequence of the disease. And so you're getting rid of smoke. It's not bad to get rid of smoke, but if the fire still burns, you still have a big problem. So you get some benefit from clearing smoke, but it's a small benefit. What I want to do, what John Vito wants to do, what Luca wants to do, what Pier Fausto wants to do, is to put out the fire. If we do that, the smoke will go away by itself. So now I want to tell you what we believe the fire is. And slowly, over the last 10 years, the whole field is coming to believe that we are right about this. Okay. Now, it was very hard to find the fire, because if you compare an Alzheimer's brain to a normal brain, there are a lot of changes. And so if you are looking for the cause of the disease, it's buried in all kinds of other things that have gone wrong with this brain as the disease progresses. But the disease starts in one place. Alzheimer's disease starts right here, and only right here. And so if you do what we did and compare this region of the brain where Alzheimer's starts with another region like here where there's no disease, then you may find something. And we did find something. Now, to understand what we found, I have to tell you what the inside of your brain cells looks like. It is not like a test tube filled with liquid with a small number of things inside. It's not like that. The inside of the cells of your brain is like this. And I will now show you a picture. Each of these things is a protein molecule, and this is how crowded they are inside your brain cell. Now, if you and I were trying to meet in a crowded place like this, we couldn't find each other unless we both were directed to the same place. And in order for your brain cells to function, you must direct these proteins to the right places so they can find each other. We call that problem a traffic problem. And if you've come from Milan, I don't have to tell you about this. Watch. Well, a city like Milan is as crowded as the inside of your brain cells. And the only reason it works at all is because traffic is directed. You have roads that go to specific places. You have vehicles that go on those roads or on the subway or whatever. And that's exactly what you have in your brain. So let's pretend that you have some used bottles to get rid of. All right? You put them in trash bags, you leave them outside, the trash truck comes, and if the driver is a good driver, the driver knows where to take them. If you are a green city, the driver will take them to the recycling station, and you can reuse them. If you are in not such a green city, the driver may take them to the dump, and eventually that might lead to toxic waste. This is exactly what happens with the fire of Alzheimer's disease in your brain. The fire is that the trucks go to the wrong place. If instead of bottles you have proteins, and the proteins need to be recycled so they can be used properly, then they are put in bags that are called vesicles, and they go to the garbage truck. And that truck, which is going to take them to the recycling plant, that truck is called the endosome. And if instead it goes here, you get toxic waste, which is plaques. And you also get the nerve cell dying, not just from this, but it dies because you are not doing this. That truck is called the endosome. And the truck driver, the good truck driver, is called retromer. It's a protein complex. And as you get older, for reasons we do not understand, you do not have enough of the good truck driver. And so, too many of the trucks go to the wrong place. But if we could give you more of this truck driver, restore it to the situation that it was like when you were young, then we would recycle again. And that is what we are doing. And we are taking two approaches. One approach is a chemical approach, to find a drug that will give you more of this. And that drug, one of the earlier versions, was made in Milan by my friend Pier Fausto Senesi and tested here on a different disease by Luca Muzio and by Gian Vito Martino. And we are now working to take this approach to Alzheimer's disease. But there's another way to do this. We could just give you this complex directly as what is called gene therapy. We could simply put more of it in. Not a drug, a gene. Let me explain, all right? So remember again that Alzheimer's starts in one place. And then over time it spreads to the rest of the brain. So we don't have to deliver a gene to the whole brain. If we could simply deliver the gene to this region of the brain, we could stop the disease there, I hope, right in its early stages. Now, this is a nerve cell in the brain, and it is talking to another nerve cell in the brain. And that communication is electrical. An electrical wave moves down this axon, but it does not connect electrically to this cell. It connects chemically by releasing a chemical into this small space between the two cells. You've heard of some of these chemicals: dopamine, acetylcholine, glutamate. These are the chemicals that transmit the electrical signal. But in Alzheimer's disease, if you have the fire, even if you don't have the smoke, these parts, the synapse of your nerve cells, begin to die. And they die backwards like this. And so you cannot transmit this electrical signal. And that's why you can't store new memories. But if this continues, the whole nerve cell will die, and you can't get it back. But if we could deliver the gene to fix this problem before the whole nerve cell dies, this should recover. And you might actually be able to restore some of the lost mental function. Amazing, but it could be true. All right? This is the part of the brain we're talking about. It's called the hippocampus. And you can see the enormous number of nerve cells that this part of the brain has. There are more connections between cells in this part of the brain, which is this big, okay? 2 millimeters, this big, all right? There are more connections in that part of the brain than there are stars in the Milky Way galaxy. You all have an entire universe in your brain. But it means we only have to fix this part. So here's how we're trying to do it. We are taking the gene for retromer. We are putting it in to a small virus, not a dangerous virus, a harmless virus. And we are putting that inside your nerve cells, and it will make more retromer. It will give you more truck drivers. And now I want to show you whether that works. So that's the approach. Take the gene, put it in a virus, put it in the body, and make more truck drivers. And the answer is it does work. And if you do this in a mouse, and remember, mice are not people, but if you do this in a mouse, all right, the first thing that happens is you clear the smoke. The plaques go down when you treat with the gene. The second thing that happens, and this is amazing, is that the mice get smarter. This is the region in the human brain that I was talking about that dies first in Alzheimer's disease. This is the same region in the mouse brain. And what we are doing is putting into that region, just that region, retromer, in a mouse model of Alzheimer's disease. And when that happens, you restore the ability of the mouse to learn. This is a normal mouse. This is an Alzheimer's mouse. It does not learn so well. This is the Alzheimer's mouse treated. It has gotten smarter. And you can see that from the electrical potential that moves down the nerves. Originally, it should move like this. In the Alzheimer's mouse, it's almost gone. But in the treated mouse, it is in red, it has come back to close to normal. So we're very excited about this because it means that if it works at all, it might be a very good thing early in the disease as far as not just stopping the disease from getting worse, but maybe helping you get a little better. So our motto, Luca, John Vito, Pier Fausto, myself, and all of our colleagues, no stone unturned. We're not only looking under the streetlight. We're trying other things, new things. We'll see if they work. Now I must finish, and I want to finish by telling you one story. Okay? The first story I want to tell you, first part of the story, is what can you do while you're waiting for us? The answer is you can do a few things to improve the health of your brain. All right? Fish oil is good. So in this part of Italy, a lot of fish in the diet, good thing. Exercise. Exercise is very good for the brain. It's good for everything of your body, so you should be doing that. All right? Keep your blood pressure low. High blood pressure is a big risk factor. Keep your blood pressure low. Don't read about politics. Especially in Italy and the United States. All right? Keep your weight down if you can, and avoid diabetes, because diabetes is a big risk factor. And stay mentally stimulated. But you're listening to me tonight, so you're okay for today. All right? Tomorrow you will hear my wife. You're okay tomorrow. After we go back to the United States, you are on your own. Stay mentally stimulated. Now, my final part of the story. The story of medicine is the story of patience. All right? Augustiner, Alzheimer's first patient, taught us that there was a disease of the brain. Joseph Meister, Louis Pasteur's patient, taught us that you could treat rabies with vaccination. Ann Miller, a school teacher in Connecticut in the United States, taught us that penicillin could cure an infection. Now I want to tell you about the most interesting patient in the world. Douglas Whitney of Port Orchard, Washington. For 50 years, the Whitney family has lived in this suburb of Seattle, Washington. And during that time, 1 out of every 2 Whitneys has died before the age of 55 from Alzheimer's disease. Because the Whitney family has the mutation that August Dieter had, the family Alzheimer's mutant gene. Doug Whitney's mother died at 51 from Alzheimer's disease. Doug Whitney's older brother died at 55 from Alzheimer's disease. 7 members of Doug Whitney's family, which is now 13 members, have died before the age of 55 from Alzheimer's disease because they had the mutation. And the ones who did not die did not inherit the mutation. Now, Doug Whitney is my age. I'm 74. Doug Whitney is alive. Doug Whitney is fine. Doug Whitney has the mutation. Doug Whitney should have died 20 years ago. Doug Whitney is perfectly fine. Something is protecting Doug Whitney. Here's his children, all right? We do not know if Emily has the mutation. She has not been tested. Here's Doug Whitney. We know that his son has the mutation. We know that his daughter does not have the mutation. If his son is protected like him, then they must have inherited the same protection, and we can find it. But we don't know that yet because he's not old enough to know, for us to know if he has the disease, if he should have had the disease. He's 40. We have to wait 10 years. 5 years anyway. Okay. Then we'll see. But I close my talk with this story because this gives hope to the whole world. Because if Doug Whitney, who by all the laws of genetics should have died 20 years ago and never got Alzheimer's disease, then someday we will succeed and you will not get Alzheimer's disease. Grazie a tutti. Of course, I'm 74 years old. So the one thing I am most worried about is that we will find the cure for Alzheimer's disease and I will forget what it is. I wonder what they would have done to Columbus if he had discovered America and then forgot where it was.
Bene, grazie mille, veramente molto stimolante questa relazione, dall'applauso immagino che l'abbiate apprezzata anche voi. Domande? Credo che insomma le cose che ci hanno detto sono, diciamo, importanti, da un certo punto di vista anche provocatorie, ma quello che è importante è che tutti sappiate che che la scienza ci sta provando, non si è data per vinta, è una malattia complicata, molto complicata, però qualche passo avanti lo si sta facendo, bisogna avere un pochino di pazienza ancora, ma insomma in qualche modo la strada per arrivare almeno a cercare di arginarla in qualche modo è tracciata. Ho visto una domanda qua, se portate il microfono, in italiano per favore.
Resto seduto. Egregio professore, ascoltando quello che ha detto, una cosa che mi ha sorpreso, perché ho sempre pensato che non fosse così, era che si muore di Alzheimer. Quando la malattia colpisce il cervello e non ci ricordiamo più niente, vorrei capire come fa a dirsi che qualcuno è morto di Alzheimer. E la seconda domanda, brevemente, che le faccio è: avete scoperto il luogo dove c'è l'incendio. Cosa vi ha portato a poter fare questa affermazione così sicura? Grazie.
So there are two questions, very good questions. I will try to answer both. I'll answer the second part first. The second question was, we discovered the part where the fire was in the brain. How can we be sure? And that's a good question. We are sure for two reasons. One is that if you look at people who are diagnosed with Alzheimer's disease early, so they just have a little bit of Alzheimer's, not much, they're mostly okay, but then they die of something else. They die of cancer or a heart attack or an accident soon after. You can look at their brain and ask, where in the brain are things dying? And it's always that one place. So that's the first reason. The second reason is you can take a mouse model for Alzheimer's disease, and with a mouse, you can simply ask, where in the mouse brain does the mouse brain start to die first in this model animal? And the answer is, it's the same place. So that's not quite the same thing as proving it, but when I tell you that that's the place in your brain where new memories are stored, it makes sense, because the earliest symptom of Alzheimer's disease is short-term memory loss. You can remember things far back, but not recent things. So I think it's a solid observation, even though it's not exactly proof. The first part of the question was, Alzheimer's is like a memory disorder. Why do people die from that? The answer is, it doesn't stay a memory disorder. So I did show you that one slide where Alzheimer's starts in one place but then begins to spread to other parts of the brain. And that's where some of the later symptoms come from, when people have Alzheimer's disease for many years. Eventually, the disease reaches parts of the brain that are necessary to keep you breathing or eating or whatever, and you die from that.
Buonasera professore, lei ha parlato solamente dell'Alzheimer, ma per il morbo di Parkinson ci sono novità?
Parkinson's disease, news about treating Parkinson's disease.
Parkinson's disease, yes. So I didn't talk about Parkinson's disease, but there are two things I can tell you. One is that it starts in a different part of the brain, but again, one part of the brain. So again, if you start early enough, you may be able to fix that particular part of the brain. That we know, and that's good. The other good thing is this, and I cannot tell you why this is true. I can only tell you that it is true. What I can tell you is, if you look at that part of the brain in someone who has Parkinson's disease, and it's just beginning, do you know what the problem is with that part of the brain? No truck drivers. Mm-hmm. It's the same problem, but in a different part of the brain. And here's the point. The point is, if you have Alzheimer's disease and you manage to live for 15 or 20 years, one of my relatives did, in the end, you will get Parkinson's disease. There is a connection between these two diseases, right? And that connection might be the truck driver. So very recently, just a year ago, we put the retromer gene into a mouse model of Parkinson's disease, and it seems to be working. Now, I cannot tell you in scientific terms why it's the same problem in a different part of the brain. I don't understand that. But if it is true, we might be able to use the Alzheimer's treatment for at least some Parkinson's patients. And we will try to do that.
Sono tante domande, allora una qua e poi una in fondo.
But all on this side, what is the matter with you? All right.
Volevo chiedere, ma visto che il problema parte sempre dallo stesso punto e poi si diffonde, quindi il problema abbiamo detto che è del camion dei rifiuti, che comincia ad essere un problema localizzato e poi si diffonde, non si riesce, seguendo la diffusione, a capire quindi qual è il problema che affligge questi camion dei rifiuti? Immagino di no, perché sennò ce l'avrebbe detto, però immagino che abbiate fatto delle osservazioni al riguardo.
So we have made some observations about that, but they have not led us to any conclusions yet. Okay. I want to be clear that you can never tell what is going to happen when you try to treat a human disease until you try in people. Mice are not people. Cells in a dish are not people. We, I think, will understand more what you are talking about when we begin to try these treatments on people. And we are hoping that will begin in about 2 years. We have safety studies to do and some other experiments that the regulatory agencies want us to do before we can put these things into people. But I think once we do and we see what happens, we'll know a lot more about that.
Domanda là in fondo. No, una prima qua, sì, arriva il microfono, arriva.
Buonasera prof, grazie degli spunti molto interessanti. La mia domanda è, nella pratica clinica, nella vita quotidiana di tutti noi, purtroppo abbiamo a che fare con conoscenti, familiari e noi sanitari anche dei pazienti con queste malattie neurodegenerative. Vorrei chiedere, lei consiglia un approccio rigido con questi pazienti, quindi con dei richiami, dei consigli molto intensi e rigidi, o un approccio più delicato visto la conoscenza della patogenesi di queste malattie neurodegenerative? Grazie.
So you ask an important question, but it is not a scientific question. It's a question for the human race. I will give you my answer, but it is not my answer as a scientist, it is my answer as a human being. For myself, I always want to know as much as possible about what I am like and what is going to happen to me. But that is not always the best thing for everybody. I think when we have a treatment for this disease, that changes. When we don't have a treatment, it is a more difficult problem. I believe that questions like, how much should these treatments cost? Should these treatments be made available to everybody? Should these treatments be short-term or carried out for the rest of your life? These are only partly medical questions. They're partly questions of economics, they're partly questions of politics, but they are mostly questions for people. What kind of life do you want? How do you want to live that life? What do you want for your children? What do you want them to know? What do you want them not to know yet? We as scientists should give you the information you need. But I feel most comfortable when those decisions are made by you, not by me.
C'era un'altra, ecco, quella signora, e poi una dietro. Prego, sempre la parte...
Volevo chiedere questo. Prima abbiamo sentito che non si sa bene la causa dell'Alzheimer, cioè perché avviene, però poi il professore ha detto che ci sono delle cose che possiamo fare per proteggerci in qualche modo dalla malattia. Volevo chiedere se si sa perché fare queste cose protegge dalla malattia, anche se non garantisce l'immunità, oppure è solo un'osservazione empirica, cioè facendo queste cose abbiamo visto che la gente si ammala di meno e non si sa perché.
Adesso devi ripeterle per vedere se hai memoria breve.
Esatto.
Okay, that's a wonderful question. You should have been a scientist. Because the question of why these things that protect the brain a bit protect the brain at all is something that we only understand a small part of. Most of this is just evidence from observation. The thing we understand best is staying mentally stimulated. You may think that means that you should do things like crossword puzzles or mental games or maybe read things in different languages. But that's not entirely true. You should do those things if they're new, not if they're the same things you've been doing for most of your life. So if you've never done crossword puzzles and now you suddenly start to do them, that's good. If you never learned English and now you want to learn English, that's good. I should learn Italian. It would be good for my brain. All right? So it's new things, and we know why that works. You remember that picture I showed you of the part of the brain where all this is happening, and there were all those nerve cells like the stars of the Milky Way galaxy. And then I showed you those cells all make connections to other cells. Well, it turns out in Alzheimer's disease, as I said, the connections are dying. But when you learn something new, you make new connections. You repair part of that brain. You make part of that brain stronger. That we know. That works, and we know why it works. For the other things, we're not so sure.
C'era un'altra domanda sempre lì in quella zona.
La ringrazio, professore, è stato molto chiaro. Avrei 2 domande. In primis ci ha dato dei dati positivi sulla terapia genica, ovviamente sono dati preclinici. Volevo chiederle se è possibile sapere quali altri dati vi aspettate di raccogliere e in quanto tempo prima di passare alla fase clinica. E la mia seconda domanda è legata a quella che ha fatto anche la signora prima di me, ed è sui consigli. Cioè, uno dei primi consigli era di assumere nella dieta acidi grassi omega 3. Volevo sapere cosa ne pensa della dieta chetogenica, visto che è uno degli argomenti di cui si sente molto parlare, e in generale una sua considerazione un po' più ampia sull'alimentazione, come possiamo curarla. Grazie.
Okay, so there were 2 parts to the question. The first part was, how soon do we think we'll be in the clinic and what do we have to do to get there? The second part had to do with a specific diet and whether it might be good for the brain. Let me answer the second part first. The diet is the ketogenic diet, and some people believe this improves brain health, and other people believe that the data are not very strong. I am a scientist, not a physician. I cannot give you medical advice or even dietary advice. For that, you should talk to your own medical professional and see what they have to say. You can read about this yourself, but I will tell you that from my own reading, this is not an established fact. Okay. The first part of the question was, how soon can we be in the clinic and what do we have to do to get there? I wish we were in the clinic yesterday. My wife always says to me, work faster. Then she asks me to take out the trash, walk the dog. How can I work faster when I'm doing all this? That never works. I try, but it never works. So it depends on the drug therapy and the gene therapy. They're at different stages. Because of work being done here at Hospital San Rafael by John Vito and Luca, on ALS, which is a different disease, but also involves the truck driving. Because of the work they are doing, I think we will be in the clinic with the gene therapy sooner. And that might be a year and a half, maybe 2 years. We will, unfortunately for Alzheimer's disease, because the people you will treat are not very sick, the treatment has to be very, very safe. And so we will have to do very expensive studies to prove that this treatment is safe in animals before we can test it in people. And I think that's going to take at least a year. And it will be very expensive. For the drug treatment, we are not so far along. I think maybe half a year to a year behind. So again, the drug will have to go through safety studies, but it's a little bit easier. If you put a gene into the brain, the gene is in the brain, and it better be safe, because you can't take it out. But if you give a drug, and the drug causes a problem, you can stop taking the drug. But we're not quite ready yet to do the safety tests of a drug. So to finish the answer, 18 months maybe for the gene therapy, 2 years to 2.5 years for the drug therapy, if everything goes well. Does anything ever go well? Right. but if everything goes well. A question from this side. I want to see if there are different types of questions.
She's a psychologist.
No.
Be careful.
Grazie professore. Volevo chiederle una domanda riguardo più ai fattori ambientali. Mi chiedevo se si era notata una differenza di percentuale di diffusione della malattia tra i diversi continenti. Ad esempio mi viene in mente il Giappone, dove c'è tanta longevità, se si è notata una differenza a livello di percentuale di diffusione di questa malattia rispetto alla popolazione.
So the question has to do with the distribution of Alzheimer's disease throughout the world and whether different populations, some of which live longer, like the Japanese, might have different rates of Alzheimer's. The answer, it's a fine question. The answer is yes, there are differences. They're not big differences for the most part, but they're real. So for example, the rate of Alzheimer's disease in Italy is better than the rate of Alzheimer's disease in the United States. We don't know why. The rate of ALS in Italy, that's not true. So there's something happening here. Maybe it's the diet. We don't know. We also know that there is one population in the world that has quite a bit less Alzheimer's disease. That is the Han Chinese population. The Han Chinese have a significantly lower rate of Alzheimer's disease. We do not know why. Now, if we knew what was protecting Doug Whitney, remember Doug Whitney? If we knew what was protecting Doug Whitney, maybe some of this would make sense. Maybe the same factor exists in Italy or in Han Chinese population or whatever. Maybe a different version of the same factor exists. We don't know. Okay? But yes, there are population differences. They're real. Okay? They're quite real. This side is catching up.
Facciamo prima qua davanti e poi andiamo dietro là. Prego.
Buonasera. Mi ricollego alla domanda che è stata fatta prima sui fattori protettivi e in particolare esercizio fisico e per quello che è il potenziamento sinaptico sostanzialmente, quindi la creazione di nuove connessioni. Volevo sapere cosa ne pensa della stimolazione elettrica nella plasticità sinaptica.
So there are two parts to your question. One has to do with sort of exercise. I'll get to that in a moment. The other has to do with brain stimulation. There are medical procedures where you put an electrode into your brain and deliver electrical impulses to the brain. They are used to treat Parkinson's disease, and they work very well. So a number of, but they don't cure the disease. They just make the symptoms better, not so much tremor and so forth. But it's logical. A lot of people have asked the question, could the same thing help with an Alzheimer's patient? Some studies are still continuing, but the ones that have been done so far, no improvement has been seen. And the electrical stimulation, my guess is not going to be a big treatment for Alzheimer's disease. Exercise, not only is exercise good, but we're beginning to understand why. A scientist at the Dana-Farber Cancer Institute in Boston, which is the leading cancer research center in the world, and which is headed by my wife, who is speaking tomorrow. So I hope you appreciate this. She doesn't. See, I don't have to understand Italian to know that. This scientist has found that exercise releases a chemical. It's a small hormone called irisin. And some very early studies suggest that irisin could be the protective factor that helps protect that part of your brain when you exercise. If that's true, it may be that you can all achieve what every American hopes for in their life, which is to take a pill that solves their problem without their having to put in any effort at all. The ultimate American dream.
C'è una domanda in fondo.
Buonasera, innanzitutto ringrazio il professore per l'intervento. Volevo capire, durante la discussione è stato citato il fatto che uno dei punti principali per la cura, per rendere efficace la cura, è la diagnosi precoce. E a che punto siamo messi con la diagnosi precoce dell'Alzheimer?
Okay, you should all be very proud. These are some of the best questions I have ever gotten for a lecture like this. This is another one. The question is, if it is better to treat these diseases early, and it is, then what is the prospect for early diagnosis? This is one of the most exciting areas of Alzheimer's disease research right now. Many people, including some of my collaborators, I do not do this work myself, are finding things in blood, for example, that can be used to do early diagnosis. These have not been fully validated yet, but all of the data I have seen look really promising. So I think it is very likely that in 5 years, maybe not more, 5 years, we will have an early diagnosis for Alzheimer's disease. Now, that is only going to be really useful if we also have a good treatment for Alzheimer's disease. It's harder to predict that, but if we're lucky, those two will converge at about the same time, and by the time we are able to say, you may get the disease, but you may not, or vice versa, we will have something to give you. That's the hope. I think there is a good chance of that.
Ci sono altre domande, una qua ancora, prego.
Buonasera, grazie mille per l'intervento. Volevo sapere, ha mostrato risultati promettenti della terapia genica su modelli di topo e volevo sapere se questa terapia genica è stata testata anche su altri modelli animali o in caso su modelli in vitro. E l'altra cosa che invece volevo sapere è se ha qualche ipotesi, secondo lei, di quale potrebbe essere il fattore protettivo per l'ultimo signore che ha mostrato, insomma. Grazie.
So the question is, the gene therapy that I showed you, that we tested in a mouse, was that tested in any other animals or in cells in a dish? And what was the protection factor? So, I can answer that question. The gene therapy has not been tested in any other animal, though it will be tested soon in a rat. There are no higher animal models. So we don't at the moment there's no monkey model, there's no dog model, there's no cow model or sheep model for this disease. But in Amsterdam, there is a colony of small pigs They're called mini pigs. They're this big. They're very cute. They have been engineered specifically not to have enough truck driver in that part of the brain. We are just beginning to get the data from that. And it looks like they are developing Alzheimer's disease or something very similar. Now that's very exciting because the pig brain is much closer to the human brain than a mouse brain is. So if we have a pig brain model for this disease, that would advance research very fast. I'm excited about that. We'll see what happens. All right? The protection, we did test this in a dish in brain cells that were derived from human patients, Alzheimer's patients, and it worked very well in human brain cells in a dish, but those are cells in a dish. The protection factor, it's close to 100% in a mouse. Don't believe that that means 100% in a person. It could mean 0 in a person. We'll have to see.
Greg, she was asking the protective factor in the family.
In the family?
The family you showed, the protective factor in the family that you showed.
In Doug Whitney's family.
Doug Whitney.
So Doug Whitney's family. So we don't know what's protecting Doug Whitney. We don't know if it's genetic, okay, because we don't know whether his children are protected. We have to wait and see. If one of them is protected, then we know there's a protective mutation somewhere in his genes. We'll find it. We can find it by comparing his genes to his daughter's genes or whatever. We don't know that yet. It can't be diet. I mean, you saw Doug Whitney. It can't be exercise. It can't be diet. Okay? It can't be no obesity. I mean, Doug Whitney looks like he's in terrible shape. But he doesn't have Alzheimer's. So it's probably something genetic, but it might be an accident. It might be a mutation that occurred when he was a baby. All right? And therefore won't be inherited by his children. We don't know. We just don't know. We do know that he seems to be completely protected from something that is normally 100% bad. That's the great thing. And as I said, I think we can be pretty sure it isn't diet and it isn't exercise. But we don't know what it is.
Bene, io direi prima di concludere questa serata, magari lei la fa personalmente la domanda così. Volevo solo ricordarvi che oggi è stato insignito del premio Nobel per la chimica Barry Sharpless, che è stato nostro ospite nel 2019 e che oggi ha preso il secondo premio Nobel per la chimica, uno dei 5 nella storia dei premi Nobel ad averne vinti 2. Quindi in qualche modo pensiamo di aver portato fortuna a Barry, se vi ricordate era stata anche aveva scoperto quel sistema enzimatico che permetteva di fare la cosiddetta green chemistry. Quindi facciamo un bel applauso a Barry Sharpless e facciamo grazie, nel salutarvi un immenso applauso a Greg e al professor Pesce.
This worked pretty well.
Grazie.